Thank you. So as the title says, I'm going to want to introduce you to categorical actions and some of their uses. So what I mean by categorical actions here, I mean actions, categorified Lie algebra actions, or categorified Lie algebra representations. So to start off, let me review a bit of classical Lie representation theory. And in the interest of time, let's restrict to the simplest Lie algebra, and at the same time the most important Lie algebra of them all, SL2. So what is SL2? SL2 has 3 dimensions, spanned by these 3 vectors. That's the standard basis, E, F, and H. Essentially upper triangular, lower triangular, and diagonal matrices. And they fulfill some relations that give you the Lie algebra structure. Then what is a representation of such a thing? Well, a representation is a finite dimensional vector space for me, complex, so I'm always working over the complex numbers, and a map from SL2 into endomorphism of that vector space. How can we analyze such a thing? A good way to do that is, well, to look at H first, because E and F are nilpotent matrices, so they don't have any interesting eigenvalues, but H is not nilpotent, so it will have interesting eigenvalues, so we can split up V into eigenvalues of H. So we call them V lambda, where lambda is into eigenspaces of H, and lambda is the eigenvalue. So, well, that's not very interesting. The interesting part is this here, the set here. So one would expect that the spectrum is some random subset of the complex numbers, but actually it's not. They're all integral. So that gives us sort of a very nice decomposition of our vector space V into subspaces. And then one can compute what E and F do. And it's an easy computation with those relations up there to figure out that E will always increase the eigenvalue by 2, F will always decrease the eigenvalue by 2. And we can put that, for example, in some diagram like this. We have the E's and the F's, and the H will always act by multiplication by lambda on any V lambda. So if you do that way, you already have a very good picture of what the representation looks like. What I want to do for today is doing the opposite. I want to take such a diagram and see it as a definition of a representation. So we can define an SL2 representation now as a bunch of vector spaces indexed by the integers, plus linear maps between them called E, F, and H, where E goes always from V lambda to V lambda plus 2, F decreases lambda by 2, and H is an endomorphism. And then there are some relations that should hold. So H should be on V lambda multiplication by lambda, and E, F, and H should have the same representation, the same relations as on the previous slide.
So your number has your finite dimension?
Everything is finite dimensional. Yeah.
So it's only finitely many lambda?
Yeah. So I didn't say that explicitly. Yeah. This is always some finite diagram. If you do infinite dimensional representations, things get much more complicated, of course. All right, and so that is the picture that we're going to categorify now. Before we do that, let's take a step back and let me just give you an idea of what categorification is about. So the basic idea of categorification is you take some problem that involves some linear algebra, has some vector spaces and stuff. You take all the vector spaces, you replace them by categories, you replace all the linear maps by functors between those categories, and so on. And so you upgrade your problem from a problem about vector spaces to a problem about categories. Why would you do such a thing? The point being is that on the level of categories, if you do this correctly, you have much more structure. On the one hand, you have more structure, on the other hand, you have more flexibility. So you have maybe a better chance of proving something on the categorical level. For instance, whereas constructions that you do on the vector spaces might unify to constructions on the categorical level. And you see pattern that you wouldn't see otherwise. And then once you do something on the categorical level, there are procedures to decategorify, to go back to vector spaces, taking K-theory and things like that. There's one caveat in this, that it's hard to choose the right category. So this, of course, only works if you choose a category that's well suited to your problem. That's more of an art than a science at the moment. What is clear is that often geometry is very useful. So instead of picking a category directly, you pick a space, and then you pick a category of sheaves or something of that space. So to summarize, categorification is the idea that you replace vector spaces by categories, you solve your problem on the level of categories, and then you decategorify back. So with that in mind, let's do that for representations. So I told you before that you should think of SL2 representation as a bunch of vector spaces. So now, instead of vector spaces, we have a bunch of categories indexed by lambda, by an integer lambda. So again, to simplify things, we do finite dimensional things, so we only have finitely many categories. Then we have some vectors E and F, not some vectors, some functors E and F going between those categories. And then we have some kind of relations between those functors. And notice that here I'm not talking about H anymore, because H is sort of irrelevant additional data that we don't need. So H's come out automatically. We get very similar pictures to what we had previously. Instead of the V lambda, we have K lambda. And instead of lowercase e's and f, we have uppercase e's and f's. But the picture is basically the same. Let's see how we can categorify the relationships. So the relations. So the first one on the first slide was EF minus FE is H. The left part is easy to categorify. The E's and F will just become uppercase. Multiplication of matrices will go to composition of functors. H, I said, we don't really need. Why? Because on category K lambda, H should just act by multiplication by lambda. So let's write it that way. Now, one last small problem, categories don't have multiplication. But remember, lambda is just an integer, and multiplication by an integer is just adding a thing to itself lambda times. So instead of writing equals lambda, you write equals a direct sum of lambda copies of the identity functor, which is exactly the same thing. And now that minus is easy to get rid of, we just put it on the other side and make a plus out of it. Was there a question?
You answered my question.
Okay. Okay, all right. In the
of copies, that's nice if lambda is positive, but maybe it's negative.
It's a good question. When lambda is negative, you do the same trick that I had just had with the minus. You just put it on the other side.
What does equal mean?
I replaced equal by being equivalent. Of course, whenever you do categorical things, you have a strong version, a weak version, and so on. So there are different versions where how you can do that, depending on what exactly you mean by equal.
No, but if you have an isomorphism, are natural compatibilities which will have.
Yeah, you can have strict versions, you can have weak versions. There are rigidity theorems. There are lots of papers that explore different directions for this. So I didn't want to be too specific here.
You have different versions, but in category, you have the additional problem usually of compatibility.
Yes. Yeah, you have to figure that out, how you want to specify that data. So that's basically the first level, and then you can have higher levels. I talked about SL2 actions. The general story works very similar. Just instead of having your categories indexed by the integers, you now have categories indexed by what's called the weight lattice of the Lie algebra G. That is some discrete data that's associated to the Lie algebra. Instead of having one pair of functors E and F, you have multiple pairs of functors EI and FI, and you have some relations between them. So in representation theoretic terms, you want to have categorified cell relations, and then again higher stuff. And that has been done. That has been used in various ways. So remember what I told you about categorification. We start with a problem about vector spaces. We categorify and then we decategorify. This has been used in that way, for example, to compute some knot invariance and categorify knot homology. What I want to talk about is sort of the opposite thing. So in some recent work with Sebenkautis, we started out with some categories. So we had some categories that are of interest for representation theory. These were some derived categories of sheaves. And then we fit them into a categorical SLN action. So we had some categories, and we made a whole SLN action out of that. The point being is then with that action, we can get additional structure on our categories. So we use the combinatorics of the action to get structure on our categories. What does a typical theorem like that look like? Okay, we start with some SL action. No matter what, we applied it to our particular one, but it's an abstract theorem. One thing I should point out that is these k lambdas are often quite complicated things. So usually they are derived categories of sheaves. In particular, they're not abelian categories. But if you want to do something with categories, often it's very nice to have abelian categories because they behave the best of all of them. And similar to this, EIs and FIs are not exact with respect to the usual T structure for the people, for the experts here. So what we did, we showed that there's an abelian refinement if you have an SLN action. So that is a choice of abelian subcategory from each a lambda in each of those k lambdas, so that the functors EI and FI restrict to those abelian subcategories. And in a certain way, there's a unique such thing. So why is that interesting? Well, as I said, abelian categories are very useful. So we started out with some categories that are interesting representation theoretically, and now we found interesting abelian subcategories, and lots of them, because we can apply them in various situations. So again, for the experts here, we're not really producing abelian categories directly. We are producing a T structure, and we show that the EI and FI are T exact.
What does the phrase any categorical SLN action mean?
It's hiding a few technical assumptions, but if you have the structure of a, to be correct, quantum affine SLN action, then you can get that under some assumptions. So you have a bunch of categories with the various relations.
It's a bunch of axioms, it's not a construction.
It's a bunch of axioms, yeah. We apply it to a specific situation then, but generally it's a bunch of axioms. Okay, so these abelian categories that we get are expected to have nice properties. In particular, some of them were already previously known in work of Bezukavnikov and collaborators, and they have been used to prove very deep theorems in representation theory. And what we do is get sort of a systematic point of view to these categories. So they have been defined in, I might say, a bit ad hoc way that was hard to digest for the average person. We provide something that's hopefully easier to digest for the average person. At least for us, it's much easier to digest. OK, so that's the story I wanted to tell you. Let me finish by showing you some other topics I'm currently thinking about where I have projects going on and that I would like to talk about to any of you who are interested in the same things. Thank you.